You can all just go away. I don't care. Oh, and that was perfect timing for the transcription to start. So the transcription recorded just started with me saying, you can all go away, I don't care. Perfect. Oh dear. Right. For the benefit of the tape, that was talking about YouTube subscribers. Oh, Connor's unsubscribed. No, he's just gone off now. That's just. Okay, so last week we started talking about file systems, and this week I want to delve a wee bit further into that. And later on, I want to talk about different types of media that files might be stored on. But before we do that, I want to have a wee think about how we might go about implementing some of these file systems. Okay, so we want to look at some of the ways that we can set up file systems, both locally and remote, and think about some of the algorithms that we can use to set them up. And as before, these are all about trade-offs. So as we've seen all through this module, whether we're looking at memory or anything else, it's all about trade-offs. You choose one thing, you lose another. So when we're thinking about file systems, it helps to have some vocabulary to do that. As ever, anything that's in blue, you absolutely definitely want to remember for the assessments. Um, so we have files, logical pieces of data, and they're stored in file systems. And we need to have some interface to that, and we saw that last week. Data will then be transferred from those file systems into memory, where it can be worked on. And it's likely that we're going to need some way of understanding what the file is. So we need the file control block, its name, its writable state, that kind of stuff. And we also have to remember that we've got different types of device. And we've talked about device drivers before and accessing different types of hardware. The same thing is going to have to happen with a file system. So the operating system hides all of that. It doesn't care whether you're saving to a hard disk, USB drive, whatever, because it just works with its device driver to give you the same style of interface. So we end up having this kind of layered idea in our file system. So the application program stays well away from the devices. It only knows about a logical file system, which then has to organize the files onto the file system, which is created on the storage device itself. That's then accessed via I/O onto the device. So this whole layer, and the nice thing about having these kinds of layers, of course, is that we can change things. I'm not really too worried if at, come on, if at this point it's a hard disk or a USB, because that's taken care of by the I/O control. This certainly doesn't care about it. And we can swap these things. We can have multiple file systems, multiple devices, multiple everything. And the nice thing is at the top where we are, we just see one logical file system. We do this every day. We plug in USB drives, all of a sudden we get a device driver for USB that needs to have input output. It needs to be added onto the file system. It needs to be organized. It needs to be shown as part of the logical file system. So in your file explorer, you see something like my USB drive. So the operating system takes care of this and takes care of it in a way that makes it unnecessary for us to think about it at all. whether we are talking about a physical hard disk, which has, in essence, iron filings glued to a disk. The disk then rotates. So this disk continually rotates, and any of you with a desktop system will hear that happening because the disk rotates all the time. And similarly, while the disk rotates, the read head will move in and out. And again, you can hear that when a hard disk is going. Part of the reasons hard disks fail because they have physical issues. The read head will hit the inside or the outside. Sometimes if you jolt them, this wee bit here will actually touch the disk because of course it's not touching normally. It uses something called the Bernoulli effect to make sure that the read head is just that wee bit above the disk so you don't scratch it all. And one of the things it will do is it will take that read head and it will hold it over here so that if the disk is moving, it won't touch it. But it's definitely not a good idea if you have a hard disk to start shaking your machine, which is something that people often forget when they have a laptop. So we can have a physical hard disk, and that's then set up to allow us to access all the data on the disk. And when we talk about a disk, actually, we usually talk about more than one. So that we just saw the top one there. But actually, there are multiple platters and multiple read heads, and you can see that on the label of the disk. How do we set those up when we've just got one large piece of real estate to save our files? We always split it up. So the read head, so this yellow one, whoops, we can split up the disks into tracks. So we've got multiple tracks in and out. And for the rotational version, for the red thing here, we split it up into sectors. And one track and one sector gives us a block, so we can move to a specific block on the disk. One thing you'll notice here is this is physically much larger than this. But they'll be set up to store the same amount of data. Under Windows anyway. Other operating systems do it differently. So they actually change, it might be how fast they rotate, so that they rotate more slowly towards the inside of the disk, or have some other fancy way of doing it. Mostly though, people have relied not on these kind of fancy tricks, but on, in essence, having smaller and smaller iron filings glued to the disk so you can get more data per inch, or by adding more cylinders, or by squeezing the tracks together, or making the blocks smaller. And that's just been the progression of disks over time that allow you to have that. So as I said, your operating system will have lots of these, whether it's a hard disk or any of the other devices that we have. We don't really care because the operating system just presents all that in one consistent way. So that's the logical way that we think of our file system versus the physical way that it's actually stored on devices. So we'll say open thread.txt, but our device driver will be told to open drive 1, cylinder 72, track 2, sector 10, and put it into a specific memory location. So that's the link between the logical thread.txt and the physical, where it's actually stored. And depending on the size it is, we might be able to get lots of it. So retrieve block 123. So we might just say, yeah, go to this one. Get this block and pick it up. So each block is numbered. But again, we've got the trade-off. So we've got this big disk set up in blocks. Do we have large blocks with lots of data in them? In which case, thread.txt, which is probably very small, will waste a lot of space in that block. Which suggests that we have smaller size blocks instead, so that small files don't waste space. But the downside of that is, because we've covered similar things before, downside of that is
Times.
say that again, sorry.
Time it takes to move. Loading times.
Not specifically loading times, because you're always going onto the disk and you're always having to move around it. What you will have to do, though, is keep track of each of the blocks. So if you have lots of blocks, but smaller, you have to keep note of them all and have to remember where they all are. And at some point, we're going to have to do that. So we're going to have to say block 123 is thread.txt. So the more blocks that we have, the more we have to keep a file. Block 1 is this, block 2 is this, block 3 is this, block 4 is this, block 5 is this. So it's about getting that balance right once again, about whether we have lots and lots of smaller ones so that we don't waste space, or fewer larger blocks where we've got less to keep track of, but we waste more space. And we looked at that before. Well, when did we look at that before in a similar way? Remember, we discussed memory and how large a chunk of memory we should have. And we had the same kind of discussion about whether we had lots and lots of smaller ones so we wasted space, or fewer bigger ones so that we had less to manage. It's the same argument here. In other words, and if we didn't, how would we know that get block 123 gives us thread.txt? We have to remember them somewhere. Now, the other thing we want to bear in mind is, of course, things like hard disks are slow, certainly compared to memory, so we might want buffers and caches. And we're going to have somewhere that, as I said, matches up the logical with the physical. Thread.txt with block 123. So we're going to have some sort of organization module to do that for us. It's also going to include all the other stuff that we saw last week that files have. Name, when last modified, read-write status, all that kind of stuff. And indeed anything else that any operating system wants to have. Now, we've said already that having these layers is really good because it allows us to add in more stuff as and when we need them. But the downside to having lots of layers is any thoughts?
Gonna slow things down.
Every time the application program has to ask the logical file system, which has to ask the file organization module, which has to ask the basic file system, which has to go out to I/O, which has to go through the device driver, which eventually gets to the device. Each one of those requests slows things down. So the layering helps us to understand, and it reduces complexity for us, but it adds overhead. But it means that we can cope with all these different types of device with different file systems as well. Okay, so how are we actually going to do this? What we're going to put in place to give us our files? Well, we've already said that devices have a boot control block. So we've already said that you can boot your hard disk from a device. So we start up the machine, it goes through the BIOS, looks for a device and says, oh look, there's an operating system on my hard disk, and it transfers to that boot control block. We've also said that we might have multiple volumes. So a volume that splits up a physical disk, or a volume that spans more than one physical disk. It doesn't really matter how we're doing it, but we need to have details of that as well. We need to keep track of how the logical layout is going to be shown. So we need to keep track of not just files, but of directories as well, and allow us to have those all available in and out and have access to them properly within our system. And depending on the type of file system, our file control block can start to grow in size. So as well as the basic information, you might want to start thinking about where it links to. So if you have something like an Oracle operating system, it won't just store information about the file, it'll store information about the indexes or about other linked table files. So you've got a whole load of stuff going on, all stored in the file control block. All stored in the file control block. And that just depends on how you set that up. So you need all these things on disk, and of course we can't work with stuff on disk, so it has to be brought in to memory. So we're going to need some sort of file structure in memory as well. So once we once we have our file system, we have to bring that in to our memory. Things like where devices are mounted, C is our hard disk, F is our network file system, U is our USB drive. However your operating system works that, you need a mount point. It then needs to know what type of system it is and what kind of information it's going to be stored in the file format of it. And then it's going to have to allow certain operations, and we spoke about them last week, open, close, that kind of stuff. So you start to end up with something like this, where our logical user thinks, well, I've got a file name. So somewhere in memory, we have a directory structure stored that says our file is in a particular directory. And in that directory is a file. So let's go into our secondary storage, our disk, get the file control block within that directory, and then bring it back into memory. How do we do that? We need to read it from a particular place, get it in, and store it in memory so that we can use it. Remember, nothing can happen until we get stuff into memory. And how does it even know where to get the stuff from? Because we've already mounted it. We've already said we have a file system on our hard disk. We have a file system on our USB. The question becomes whether we set those up at the beginning, so whether we mount the disks when we start up, which is common for our internal devices, or whether we mount them on an ad hoc basis. Put in a USB, stick in a DVD, add on an external USB hard drive. It really doesn't matter, but we need to have some way of putting those on as and when they are required, not just at the beginning. And sometimes you'll have noticed when you install things, the operating system gets upset. So Windows, for example, will quite commonly, when you put in a USB drive, will complain and say, can I check this file system? Quite often what's happened actually is that you've used a USB in another machine, quite often with a different operating system, and that stores different data on the drive. Our operating system gets upset and confused and says, what's going on here? And wants to go and check it. And you can test that, because the next time it tells you, can I check the disk? Tell it no and have a look. And you probably find that files are actually there quite happily. Sometimes though, it's completely blocked and you can't do anything with it. Either because your operating system doesn't understand the file system. So you've plugged a USB into a Mac and formatted it for a Mac, and then you try and plug it into a Windows machine. And the Windows machine simply doesn't understand the file system. Or because you've got a physical issue with all that metadata that you're storing on the disk. All of your directory structures and file control blocks and stuff. If something happens to those on the disk, you struggle to see the rest of the files on the disk. And because you've got no way of accessing them. You've no way of knowing where things are. And you start to end up with things like this. Bad sectors or problems detected, or whatever it happens to be. And I'm sure at least some of you have seen at least some of these error messages. Okay, we're happy with that so far. So, how are we going to set up these structures? How, for example, are we going to actually implement a directory structure? Well, we could just have a list. Fred.txt is in Flintstone's directory. Wilma.txt is in Flintstone's directory. Wilma.txt is in Rubble directory. And every time we want something, we just go through and figure out where it is, just being through a list. Problem with a linear list, it takes ages to go through. Yep. James had an error of this type yesterday. So we can start to use other types of organizational system. And if you know what a linked list or a B tree is, great. If you don't worry about them. It's just a fast way of accessing data. Those of you doing things like algorithms and structures will absolutely understand what these are. But you can just trust me that they speed things up. B's for binary in this case. There's other ways of approaching it as well. We can use something called a hash table. And a hash is basically a fancy mathematical function. So you can take a piece of data, apply a hash function, and what it does is it gives you a unique number. And only the data that you feed it will create that unique number. So you feed in Fred.txt and it gives you a unique number, which you can then very quickly get to. Because if you already have the hash number that's unique, means you can get to that very quickly. If you already know that you have to go to number 816, and you don't have to search through 1 through 815 like a linear tree, it's much quicker. Downside with a hash is it's very complicated. It's a complicated mathematical function, so it takes time. And also creating the function in the first place is really hard, particularly to do what I've just said they do, in that you want a unique number and you can't always get a unique number. So you get a collision. So you have to put that into your structure as well and think, what happens if I feed in the same name and I get the two things out? We also have to think about where we put stuff on our disk. And again, we've talked about this before. When did we talk about contiguous allocation before? Anyone remember? It's the same arguments and the same approaches that we took to memory, where we said when we load a file into memory, does it all have to be contiguous? Does it all have to follow one after the other in memory? And we've got the same type of arguments for implementing our file systems. Do we say that all our files have to stay in one huge block on the disk? Or are we happy that they are split out? If we have contiguous allocation, it's dead simple. We just say go there and read 10 blocks. That's our whole file and we're done. But in the same way as we did with memory, we can start getting holes in the disk. We can start struggling to find free space. Even if we've got lots of space, it might be split up into smaller things. We might end up with editing a file, making it bigger, and then finding out we can't save it back into the same place. So we have to take a whole file and put it somewhere else on the disk. So it starts to get tricky. The fragmentation builds in and you start to having to defragment disks to allow you to speed them up. But as I say, it is really, really simple. All we do is say, have a file, say where it starts, say how long it is, and then we can very quickly pick up our files on the disk. But what we end up with is things like this. Holes in our file system. If we have a file that's 7 blocks long, we currently can't store it because we've got 4 here, we've got 6 here, we've got 2 here, and we've got 3 here, so we've got plenty of space, but we don't have 6 contiguous blocks. So it's nice and simple, but there are problems with it. So maybe we want to move to something like this, where we have an extent-based system. So you start off with your file, and then when it gets bigger, you allocate some more. So you say, okay, I'm going to have a file. I reckon it's going to be 10 blocks on my disk. Here's 10 blocks. And you work on it for a while and your file gets bigger. So you say, okay, give me another 5 blocks. And every time your file gets bigger, you extend it out. That gives you some of the advantages of contiguous in that at least the extents are all together. So you can say, okay, it starts here and it's 10 blocks long, go get me all of that. But you start to create some more complexity because you have to point to the new part of the file. Because the file now consists of one or more extents. So the obvious next step from that extent is, well, if we're already doing that, if we already have to point from one part to the next part, to the next part, to the next part, why not just link them in the first place? So rather than saying, oh, reserve me 10, just say, nah, start off, give me 1. And then we need another one, point to the next block, and then the next block, and then the next block. And it doesn't matter where in the disk we are, we start off with 1, we point to the next one, we point to the next one, we point to the next one, and every time we keep pointing to the next one until we are at the end. And we have something called a nil pointer or a null pointer. We're not pointing anything at the end. So we only take the space that we need. And you can get Solitaire still, David. Nice to know I'm talking about file systems and you're talking about Solitaire. You can also get it on Android now. They've brought the whole Windows XP games onto Android. Install them there. I think you can get them in the Windows Store as well. However, file systems with a linked method, there's no space lost. You're not worried about suddenly finding the space. If the space exists, we can use it. Although that does suggest we have to remember where that free space is. We have to know which of those blocks are empty. And that's the white ones in this case rather than the grey ones. it might take time. So instead of just saying, go to position 14 and read 3 blocks, it has to say, go to 0 and then go to 23 and then go to 3 and then go to 24. And if you remember how our hard disk is, what we're really saying for this type of system is go here, and then go here, and then go here, and then go here. And each time we do that, the disk has to rotate and the head has to go in and out, and that takes time. We also have the issue of what happens if one of the blocks in that file gets corrupted. What if you're halfway through the file and your pointer to the next block becomes corrupted? All of a sudden your file stops halfway through and you don't know where the rest of the stuff is. So just one block can kill the whole file. How about then, rather than storing the link within the block itself, we have a table somewhere. And the table says, okay, Fred.txt has got 1, 8, 16, and 4. So that file has been allocated 1, 8, 16, and 4. And we keep that file allocation table somewhere that says, okay, this file has got these things. Now, the nice thing about having a file allocation table is it works in the same way. So each time you add something on, it gets added onto your file allocation table and you know where the next block is. But it's in one space. So rather than being all over the disk and stored per block, you can store it in a nice wee table. Which also means that you can bring it into memory, which helps speed up getting to where things are. But of course, it also means that you've got one point of failure. And the number of times in the early days when the file allocation table died and then you couldn't get access to the disk were too many to count. So you might want to keep a backup of the file allocation table somewhere else on the disk. And you remember what I said about physically damaging disks. So you might have a strategy where you keep one copy of the file allocation table on the outside edge and one copy on the inside, just so they're physically far apart in case of any physical damage. So there's all sorts of things like that where you can set them up. But when you come down to it, you have a linked list. You point to the next one, and then the next one, and then the next one, just like that. Until finally you've read in all the adventure you've read in all the file. Sorry, I'm laughing because you guys are still talking about Solitaire and how it's on Windows 11, and that's the best thing about Windows 11. So here we have it on the disk, and we follow each block one after the other. Here we have it in a file allocation table. So we can see here we've got a table where the disk blocks are numbered. And we said earlier what difference does it make how big the blocks are? Well, it makes a difference into how big this table is. So instead of having the pointer stored within the block, so you start at 9 and 9 says go to 16, and 16 says go to 1, and 1 says go to 10, and 10 says go to 25, 25 says -1, which means no more. Instead of having that, you have a similar thing, but in one table. So the file starts at 217, 217 goes to 618, 618 goes to 339, and then has a -1 to stop in there too. So same kind of idea, but you get the issue with block size. Make it too small, and you have lots and lots of blocks in a huge file allocation table. Make the blocks too large and you have a smaller file allocation table and you waste lots of space. And you might have seen things like FAT32 and FAT64, and that's where you have a 32-bit number for the number of blocks or a 64-bit number for the number of blocks to give you a larger amount to go to. Because think of what happened when you went from a 100 gig disk to a 1 terabyte disk. Number of blocks multiplied by 10. So the number of blocks that you had to keep track of multiplied by 10. So you either had 10 times as many blocks, or each block was 10 times the size. So this is a nice simple way of doing it. It's actually used on pretty much every USB drive that you'll find because it's nice and simple and it's good for smaller file systems. But as they start to get bigger, all of these things come into play about size of block and how many entries you have. So you might want to do an indexed allocation. So instead of having them linked, each one instead has an index block. So you say this file starts at 19. And when you go to 19, it says, okay, what you're going to need is 9, 16, 1, 20, 25. So each starting block points to all the blocks that it's going to need. Again, slight slowing down here because all you've got is the first one. And to get the rest of them, you have to read the first one and then queue those up to go and get them from the disk. So you only need the index table, one for each file, but it's random. And then you link from one to the other once you're in there. And there's nothing to say that you can't have double indexes. So here we've got a certain number of index links. What if we have more than the 1, 2, 3, 4, 5, 6, 7, 8 links that you've got there? Well, maybe the last one can have its own index block, which has the next 8, which has the next 8. So you get 2-level indexes. So you can have an outer index, which goes to an index table, which then links to the file itself. So it starts getting more and more complicated until you end up with things like this, a Unix UFS, Universal File System. And you see that it's made some choices. It's chosen to have a 4K block. So each block is 4K in size, and the address is 32 bits. So that immediately gives you a limit on the size of this device. So 2 to the 32 times 4K is the largest amount of data that you can store using UFS. And I'll let you work that out yourself. It also uses a combination. So there are direct blocks where you just go straight to the data. It has single indirect. So the first block takes you to the next blocks. And then you've got double indirect. One block takes you to the next index, takes you finally to the data. And you would set these up based on the need. You know, ls on Unix is an executable file that gives you a list of files on your current directory. Used quite a lot. You probably want to get at that quickly, so you have it directly linked. My backup from 2016.gzip probably hasn't used that often. I'm happy with triple indirect. And the file system can actually start to tune that itself. So things that it's using more often, it can move about within its indices. If you choose to do that in the operating system. So all of these things are choices that you make. not always unique choices. And you might find, for example, that your main disk uses a different file system from your USB drive, and it'll certainly use a different file system on if you happen to have a DVD player, a DVD drive attached. So you can have multiple file systems all on the one device for different reasons. Why would you bother having lots of indices if you're doing a DVD? The DVD starts at the beginning and you go through. And if you need to fast forward, you jump up 4 blocks at a time instead of 1. And if you want to go to a different chapter, it'll wait until you go to block 1000. But it's very simple. Start at the beginning and go through, in essence, because it's a DVD. You're watching a video in order. So you'll have different file systems based on different use cases, quite often all linked to the same operating system, depending on what it is you need to do, whether it's about performance or whether it's about whatever. And in fact, having the more complicated file system for a DVD would actually cut the performance. Can you imagine the DVD if it went to the outside and then had to zoom in and then move to, and it was all over the place? Can you imagine the DVD having to do all that reading? It just would be nonsense. So we choose what we're doing depending on the type of workload that we have. And we can start to work those out. We can start to work out how long it takes us. And the one truism is if we go to an external device, it will be slower than getting to memory. And we can start putting these in, there's that Core i7 running at 3.4 gigahertz, and we can see how many CPU instructions we lose just in getting some I/O. Those numbers will always change depending on your CPU and your I/O and all that kind of stuff. But one disk I/O with 630 million instructions. So you do one disk I/O, it's the same as doing 630 million instructions in CPU. I think the numbers there speak for themselves. I mentioned earlier that when we have our file system, we're going to have some spaces in it. If we split it up into blocks, we're going to have blocks that aren't used, and we need to know where they are. So one of the ways we can do that is just have a bitmap. So in essence, 1 bit for every block. If it's unused, it's a 0. If it's used, it's a 1. Or vice versa. It actually doesn't matter. Here, if it's a 1, it's free. And if it's a 0, it's used. Who cares, as long as everyone chooses which way around is which. So we can start to go through our bitmap and find free space. But of course, we're going to need space for our bitmap as well, and we can work out how much space we are going to need. Here we've got one, and it's the same as that Unix one. It's a 4K block size, which is 2 to the 12. You'll remember that from computing systems last year. We've got a 1 terabyte disk. That's 2 to the 40. So the number of blocks that we need to use the whole disk is 2 to the 40 divided by 2 to the 12. And that just gives us a number of blocks. And from that, we get 2 to the 28, which is 256 megabytes of bitmap. Quite a lot. Quite a lot just to remember which block's been used on disk and which hasn't. If you get a 4 gig of memory in your machine and you're using 1/16 of it for a 1 terabyte disk, just to remember which bits are used and which aren't, that seems like quite a lot to me. So maybe we use the same sort of thing that we did for the files, but instead of linking each file and having the block pointing to the next one, maybe we have a linked list for the unused ones. So we just store the first unused one, which points to the next unused one, which points to the next unused one. And if we need a block, we go to this free list, we take the first one on the list, We take a note of what that's pointing to, and that then becomes our next first free block. That's much, much quicker. So all we would do if we have this kind of free space thing, so here we'll get a free space, and here grey is free. So we just say it starts at 2, 2 points to 3, 3 points to 4, and so on and so on. If we need a block, we say, okay, we are taking block 2. We know it's block 2 because that's our head. That's no longer free. So we take this 3 that it's pointing to and make that the header. So it's dead, dead quick. That yellow is not that easy to see, is it? Is it just me, or is it not that easy to see?
You can make it a wee bit thicker. I think it'd be easier.
No, I've only got colour options. I don't have
But-
thickness.
But red.
You get the idea. And again, as we've done before, we can start to finesse that rather than get the next block, we can get the next X number of blocks to group them up, because we quite often want more than one. And we can also start taking note of how many we have. So all of these things can be finessed to allow us to get more to what we need for our own scenario. So we can get to the point where we have something called a space map, and that's used, ZFS is used on massive IBM mainframes, which have terabyte upon terabyte of data storage. So of course their file system will be different to my machine here with a 256 gig SSD. Of course it is, because they've got an awful lot more data to store. So they can split them up into meters lab units and manage multiple ones of those. And it doesn't really matter what that is. The point is, we have to take different approaches for different things, all to ensure that we get the best performance that we can for our workload, which is why you see quite a lot of differences depending what it is you're doing on your machine. So if, for example, you've got a Windows machine, it's set up for a general purpose workload, combination of big and small files, different types of application that are running. So when you get to the edge of that, massive files for video rendering, you'll start to see the file system struggle a wee bit because it's not used to having to cope with 4 or 8 gigabyte files. Which is why sometimes on high-end workstations, you might actually have 2 physical devices, one for your operating system and your applications, one for data, and you actually use a different file system for that data just to cope with these sorts of things. And of course, as with most of this stuff, we can put other things into place. We can start putting buffers in. If we think we're going to use stuff again, like that ls command, we'll keep it in memory. Make some space available for things that we've got and are likely to use again. If I type ls at the command line, I'm probably going to do it again to get a, I'll do ls and then I'll do ls star.txt or whatever it happens to be. So keep that in memory in a buffer. Maybe sometimes we can think ahead. If I'm getting block 1, odds are I'm going to get block 2 as well. So while I'm getting block 1, why not get block 2 and have it ready? And if we don't need it, well, okay, never mind. But if we do need it, all of a sudden it's already there to go. So we can read ahead. So we can start to use a lot of techniques to allow us to get better efficiency and better performance. Any questions?
Nope.
All happy? Okay, so as I said, we're going to do 2 today. That was implementing file systems, and I want to do a short one on mass storage structures. So we will do that, but I think you need a break because some of you want to go and play solitaire if nothing else. So I'll give you 10 minutes to go and play some solitaire, and I'll see you back here in, whoops, in 10. Would MD win at solitaire? Assume that's what you're all running away to do anyway. Okay, MD thought of anything they want to ask before we move on to our next part?
What's the difference between volumes and partitions?
So partition is a physical split. So you can take a disk and split it into multiple partitions. So you can take a disk and have C, D, and E.
Mhm.
A volume is a logical split. So your E drive could be a data volume, but you could then add another disk, another physical disk, and extend the E drive to have more data.
Yeah, so it spans multiple disks.
It
Or could.
may or it may not, but a volume is a logical way of thinking about it. Partition is a physical way of splitting it. And
Okay.
it's not physically split, but you know what I mean. It's
Aye.
set up as a different device in how you would see it.
Thanks. That's all I had to ask.
Anyone else? Okay. But I want to have a look at some mass storage systems, and I stress some because clearly there's too many for us to go over in detail. So I just want to look at some, as usual, of the choices that we make when we set these things up and how how you might go about setting them up and using them. So as before, we'll look at some of the ways that we can approach it and look at the trade-offs that we make, because of course, once again, it's going to be about trade-offs. So we just spoke there about a hard disk, magnetic disk. As I say, it's about gluing iron filings to a platter. And if you did the wee experiment in primary school where you get a horseshoe
Sorry, are
magnet
you
knife.
recording this part? Are
Say
you
that again,
recording
sorry?
this part? Are you going to record this part?
I left the recording going, he says,
Was it
hopefully.
sorry? No worries.
Suddenly worrying. Yeah, it's still recording. So yeah, you'll just have to fast forward through the 10-minute break as usual. Yeah, so I've completely forgotten what I was saying.
The iron shavings experiment in
Oh
school.
yeah. So you played with it, maybe played with it in school, and if you had one end of the magnet, the iron filings would go one way, and if you had the other end, they would go a different way. And that's basically all a magnetic disk is. You magnetize it, and if they point one way, it's a 1, if they point the other way, it's a 0. And that's, in essence, all that you're doing there. The magic comes because iron filings are very small and the disks are rotating very quickly. But there's still a limit, so we have to think about how fast we can get data off the drive onto the computer, and that's the transfer rate. We have to think about that head that's moving about and the disk that's rotating. So the time for the disk to rotate and the head to go to the right place, that's the positioning time. And we can split that up into the seek time, which is the head, and the rotational latency, which is the disk. And as I said earlier, sometimes the head hits the disk. That's not a good thing. Normally it doesn't. The Bernoulli effect keeps it away. We've also got disks that aren't attached all the time that we can attach and remove. And we've got different ways of attaching things. And you can see some of them on the screen there. And because we have all these different types of device attached in different ways, we need something in between, and that's the disk controller. So the computer talks to the disk controller, and the disk controller then sorts out how it gets things. So we end up with a hard disk, as you've just seen, that looks something like this, with multiple platters, multiple read-write heads. These are all rotating, and this is moving in and out. so that we can get access to all the data, all the spaces on the disk. As ever, technology moves on. This slide is nearly 10 years old now. I think you would struggle to find a 30 gigabyte magnetic disk these days, although you would have no problems getting 4 or 8 terabyte disks now. But one of the things you want to look out for is how you go about getting your fastest access. So you want to look at the transfer rate, how fast the bus is. You want to look at the seek time and the rotational latency. So if you get a disk that spins more quickly, clearly it doesn't take as long to get under the head. So the latency goes down as the revolutions per minute goes up. And you can start to work out, using all of these things, how long it will take to get a particular piece of data. And you've got an example on the screen now. Don't take too much notice of the calculations, other than to say that's how you calculate them and that's how you plug them into any device that you have. Whether the ones on the slides are accurate for now is up for debate. But either way, we can calculate our overall access latency. So it's the seek time, which you remember was moving the disk arm in and out, plus the rotational latency, how long it takes the disk to turn. So you get access latency or average access time depending on how fast the head can move in and out and how fast the disk rotates. So we can start to get an idea of an average time taken to go to a particular part on the disk. And then we have to add on the I/O time, how long it actually takes to get the data off the disk and into memory. And you can start to add all that up. So here it's a 4K block, 7200 RPM disk, 5 millisecond seek time, 1 gigabit per second transfer rate, 0.1 millisecond controller overhead. Add them all together and you can say that is the I/O time for this particular disk, for this particular controller, for this particular rev per minute. You get the idea. So you can calculate them for all the disks, and people do. And even though we look at it and think 9.3 milliseconds, it seems an age compared to, how many CPU instructions you could take. Well, we are getting better. One of the first hard disks, for example, so the disk that you're about to see is a 5 megabyte hard disk, not giga or tera, 5 megabyte. And it looked like that. And weirdly, you can still actually see the stuff that we're talking about. So you can actually see all these platters. They're still there, they're still rotating. You can still see the heads. It just so happens it's in a box about the size of, a double fridge freezer. And yes, that is it getting loaded onto a plane using a forklift. So that's nearly 70 years old, that one. 5 megabyte. Oh, sorry. Actually, I lied. It's not 5 megabyte. It's 5 million. The IBM at that time didn't use bytes. They used 7-bit characters. So it was 5 million 7-bit characters. They didn't have the parity bit. They didn't use ASCII. It was just 7 bits. Basically, if you look at ASCII up to from 0 to 128, that's the characters. 0 to 127, that's the characters they used on this. But as I say, you can still see the platters. They had 50 of them. They weren't, that size for your hard disk. They weren't 3.5 inch. They were 24 inch, 2 feet, 60 centimeters, something like that. And it took a second for access. And that was fast in 1956. We're moving on now to more, sorry, we're making a change now. So my machine uses an SSD. It's solid state, so I don't need to worry about a disk rotating or speed. It's more about memory, internal memory or USB memory. And of course, that means that it's much faster and it's much faster to access. But of course, memory is more expensive, so the capacity is lower. And I said 256 in this. It might even be 128. I can't remember. But you know, it's a long way from a 4 terabyte hard disk. But it's much, much faster. However, it wears out in the same way as hard disks do, because they are still physical. And those of you that have an SSD will probably have something called leveling software, because there's only so many read-write cycles you can do on each memory cell. So the leveling software just makes sure that you use all the disk. In other words, it levels out the access. But eventually you'll use them up and the disk will stop. But certainly no seek time, no rotational latency, much faster, but more expensive, less space, and the lifespan can be low. We've also got magnetic tape. We talked about that, I think, 2 weeks ago. And people think that's a historical thing, but it's not. We're still using it, and I spoke to you about it before and showed you the videos. The only thing I'd say about this slide is, again, we're slightly out of date. With 200 gig to 1.5 terabyte, well, now you're talking 1 to 20 terabytes probably. But cheap, stores a ton of data from next to nothing. It just takes time. And that's the triangle you usually have. Speed, cost, size. Pick two. You can have it cheap and a lot of storage, but it will be slow. You can have it expensive and a lot of storage, and it will be fast. You can't have cheap, fast, and lots. As we were just talking about, we can split up our physical disk into a logical structure. So we have a logical block. And we split up our storage device into these logical blocks and we map them. We then connect them onto our device using an I/O bus. And we have several of those. Ones you're familiar with, like USB. Some you might be familiar with, like Lightning or Firewire. Some you may or may not be familiar with, like SCSI or Fiber. David says M2 SSDs are quick, cheap, and fast. They are cheaper than they used to be, yeah, but they're still more expensive than the equivalent hard disk. So again, the cost, speed, size comes into play. For an equivalent size, SSD is still more expensive and faster. Hard disk is less expensive and slower. So yeah, we have lots of different types for lots of different scenarios. So quite a lot of larger systems will use SCSI. Basically, you can connect 16 different devices just on one cable. So you can start to build up what we call a storage area network. So we're familiar with a local area network where we connect our machines together. Well, why can't we connect storage together on a storage area network? If we already have disintermediated between us and the actual storage, because all we think about is a logical file system, and we've got all these layers in between, there's nothing that says that has to be on our machine. There's nothing that says it has to be in this country. All we need is another layer in there to say, well, actually, it's in some data center somewhere on a storage area network And if you want a colloquial name for that, you can say it's on the cloud. Because that's all it is. The cloud isn't some nebulous thing. It's just a computer somewhere else. So we can start setting up these storage networks. And the same things apply when we're talking about implementing them, but on a bigger scale, because we'll have more ports, more disks, more ways of accessing them. Particularly when you start to get large storage area networks that you then need to double because you need to duplicate them or back them up or anything else that you're having to do. So you end up with things like this. Your clients and servers are on your local or wide area network, but there's nothing to say that you can't then connect to a storage area network, which has a whole bunch of storage arrays, whether it's SSDs or hard disks or tapes. And again, you don't need to know about it. My Windows File Explorer has a drive C, which is my local SSD. It's got a drive S, no, it's a drive M, which is my machine happens to allow me to attach a micro SD card natively because of the Surface. So I've put a micro SD card in it, and that's M. And it's also got OneDrive. So all my OneDrive is in my File Explorer, and I don't need to think about the fact that it's going through the internet, through the cloud, somewhere into one of Microsoft's storage libraries. All I say is bring in the file I need. Bring in my storage structures PowerPoint presentation. Because this thing you're looking at is stored on OneDrive. And I didn't need to do anything special to get it. I just clicked on it, same as always. Of course, if you're starting to set up something like OneDrive or Google Drive or Dropbox or any of these other things, you start to scale up the problems. We've already spoken about how slow it can be to get data from one of these devices. Well, what if you've got lots of devices and you've got lots of users all trying to access them as well? So you might want to change how you're connected. Instead of having a bit of copper, you might want to put in some fiber. So optical connections that will run much faster. Maybe you want to change how you're setting up the data. So you could, for example, instead of having the file on one physical disk, how about you had the file over 10 physical disks? So if you needed 10 blocks, you didn't have to wait for one device to give you 10 blocks. You waited for 10 devices to give you one block, which can happen in parallel. Maybe you could speed it up that way. So there's all sorts of things that have been put in here to try and speed stuff up so that our storage networks can be faster. And we can bring that into our own local areas. I've got NAS. I've got a network attached storage server. What is it? It's a Western Digital drive attached to my router via an RJ45 cable, a 1 gigabit cable. And that's attached to my File Explorer too. It's drive L for LAN because I've got a huge imagination. And if I save things to drive L, they go to that box instead. And when I set up backups, I say save to drive L because it's a physically different box and I back up my data to a physically different box. But the layering stuff that we saw before works in the same way. I don't have to think about it other than saying, oh no, it's going to L rather than C, or rather than M, or rather than O for OneDrive. There'll be other things that you have to put in. You know, you might have to talk about TCP connections and you network guys will know what that is. If you're not a network guy, you don't need to know what it is. It's a network protocol that allows you to send data over a network. But again, the operating system will take care of that for you. Oops. Okay, is everyone happy with that just before we do the last bit?
Yep, all good.
Okay, so here's another question for you. Is the fastest way to access the disk to service requests in the order that they come? So say even on your local system, you've got Notebook and you've got Notepad and you've got Word and you've got Excel. And they all try to open a file. Fred.txt, Barney.doc, Wilma.xls. Do you do them in the order that's coming? Or do you start to think about, well, hang on, we have got a disk. And that disk is rotating. And it's split up into different cylinders. And of course, we've got a read head coming in here and moving in and out. Well, what if Fred is down here and Barney is up here and Wilma is over here? Do you wait until the disk is rotated to get to Fred here and move the head right the way into the middle and get Fred, and then wait until it rotates again because it's got to go all the way from here to here? Wait until it rotates again, bring the disk head all the way back out again to the edge to get Barney, and then go back in again to get Wilma? Or do you think, well, actually, I'm starting here? Maybe the best thing to do is, as Barney's about to pass there anyway, maybe I get Barney first. And then the next one that will come is Wilma. And that's starting to get very busy. But the disk is rotating this way. So the next one that comes is Wilma. So we move the head in a wee bit further and we get Wilma. And then finally, the last one that's going to come is Fred here. He's got to go all the way around there. So instead of getting Fred, Barney, Wilma, we get Barney, Wilma, Fred. That's what we mean by disk scheduling. Maybe we can minimize the time we take to go to different places on the disk by being smart about it and thinking about where physically we're going to be. Because there's lots of requests, and we're just thinking about our applications, but we already know that there's hundreds of processes running on our machine. Maybe some of them are trying to access the disk as well. Maybe they're trying to get things. Maybe we'll get a multi-user system where there's multiple users trying to access the disk. So we can end up with an I/O queue that looks like this. We know where we are on the disk. And if we just go first come, first served, all we're doing is we're starting at 53 there. We have to go to 98, then 183, and then all the way back, and then all the way in, and then all the way, and we're zooming around here. That's what happens when we use first come, first served. We have to do an awful lot more moving than perhaps we would want to. So in the same ways we've done before, we might want to think about different algorithms that we could use. Shortest seek time first, for example. So we have the same queue, we know where we are, and if we're at 53, we go, well, okay, if we're at 53, what's closest? 65, right? We'll get 65, then we'll get 67, And then we'll go back to 37 and 14, and then you see it's a more gentle approach. And we're getting things, rather than zigzagging all over the place, we just get them in a nice order. Downsides, of course. Remember when we did shortest job first, that if jobs came in that were shorter, some things kept getting bumped. We can have the same sort of thing with this. If new jobs come in and they're always closer to this side, we might never get up to 183 here. It might just continue serving the stuff that's down here. So we need to build in stuff to make sure that everything gets quicker. So in the same way as we put in aging for our processes, maybe we put in aging for our IO requests to say, okay, no, that's more priority now. What about another approach? What if we just do scan? So rather than this approach where we move around all over the place, maybe we just start at the beginning and work our way through. So we go to the start, we work our way through, we pick up every request that's in the queue, and we go to the start again. And we pick up every request that's in the queue and just work our way through so that everything gets a shot and we're always just going one way. It's kind of like being in a lift. So the lift just goes up and down. And you just get on wherever the lift happens to get you. There can be issues in terms of how long it takes. So it is nice to think, well, we're just starting there and we'll finally get to 183. But we've only got 1, 2, 3, 4, 5 requests here. What if we had 50 or 500 or 5,000? So we could start here and we might need to do 5,000 requests before we get here. So it can cause issues with speed as well. So maybe we can do something called C-scan. Remember, we have cylinders, and that's what the C is for. So we still go from one end to the other and we service requests. But this one, we go straight to the back again. So it's not like a lift anymore. So we're not going from one and back and one and back. It's like a lift that's circular. So it will go up and then immediately go to the bottom and it won't wait for anybody. And actually you see that in lifts as well. Have you ever been in a place, you press the button, you know the lifts can pass because you can see the number and it doesn't stop. It's the same idea. It jumps past because it knows that most people are waiting at the ground floor. So it goes past and then it goes up again. And that's what C-span does. So scan, starts at one end, goes to the end, and then it reverses. So it, oops. So you can see here, this is on its way back and it's going backwards. And then it's going forwards. And then it goes backwards. And then it'll go forwards. C-scan always goes one way. So it'll work its way forwards and then just zoom back, not doing anything. And then it'll work its way forward again. And it turns out that gives you a more uniform wait time. We can also do C-look. So here what we're saying is we're working our way through. We get to 183, which is one of our requests, and we work to the end of the disk, which is 199. Why? There's nothing in our list that suggests we need anything above 183, so why don't we just immediately zoom back? And in fact, why are we zooming back to 0 if our first request is at 14? Why don't we just go from there straight back to there? And that's what C-look does. It ignores all the extraneous bits at the end. And again, this has real physical knock-ons because you're physically moving a read head. So this time that you're cutting off actually helps. So as with other algorithms we've looked at, we need to decide, or the operating system writers need to decide what they're going to have. And it will depend again on the type of job that you have. So if you've got lots of disk loading, scan or C-scan. SSTF, shortest seek time first. If you've got a fairly low load, that actually works quite well. And it has the benefit of seeming like common sense. Although the only two things we know about common sense is it's not common and it rarely has much sense involved. So SSTF used a lot, heavier disk loads, scan and C-scan, but it really depends on the load of your machine. So a desktop machine will choose a different approach to a server. So a desktop operating system would use a different approach to a server operating system. And in fact, these things are so important that there's actually a third-party market for them. Not for your Windows box. But if you're running a big server farm, or you're running a big mainframe, and you can come up with something that allows you to trim a millisecond off every access to the disk. Think about how much performance gain that is. So people actually sell different disk scheduling algorithms as separate modules, and you can add them in. Some companies actually use that. You can buy a machine with one disk scheduling algorithm, or you can pay more to get a more efficient one. You know, it literally costs them nothing more. And finally, we want to, everybody happy with that before we, you're still on mute, Connor, or you're eating your mic, I'm not quite sure which. I can see your lips moving, but you weren't coming through. No, still not coming through. Nirvana album, I think. No, we're doing Scottish acts this term. Maybe next term. Okay. So last thing we want to think about, I think it's the last thing we want to think about, is disk management. How we actually format the disk. Because remember what we've got. A huge platter with iron filings glued to it. There's nothing that says it's set up as cylinders or how many cylinders there are. There's nothing that says that it's set up with sectors or how many sectors there are. We need to do that. We need to decide how many we are going to use. And we need to actually imprint that on the disk. That's what formatting does. Divides it into the sectors that it can use and allows us to have access to those. We can then, as per Connor's question, take all of those sectors that we've set up and we can put them into one chunk, and each chunk is a partition, so it's a logical disk. And there's nothing that's, quite often there's only one, so there's one partition on one disk, certainly for desktop machines, but there's nothing to say that it has to be. Have I lost my camera? I'm not seeing myself on the screen. No, I'm fine. Wonder why I'm not seeing myself. So there's nothing that says it has to be one, although quite commonly for desktop machines it is. And that's part of the thing, of course, about why you do this type of module. because quite often your experience is limited to the sorts of machines that you use. For larger machines, for servers, for mainframes, for all that kind of stuff, there's no limit on how this can be set up. So we partition our sectors into groups, and that gives us a logical disk. And then we decide what type of file system we're going to put on them. And we looked at file systems earlier, and there's nothing that says that each partition has to have the same file system. So again, quite commonly we have. Sometimes you'll buy a machine and it will have a big disk C and it'll have a drive D that talks about, and it calls itself a recovery disk because it's already partitioned into two different logical disks. It's the same machine, same drive, same physical drive, but it uses a different thing so that when you hit a special key on your BIOS, it goes to a different partition and restores your machine. Now, we've split our machine into blocks. So we've split the drive into blocks, but actually quite often we'll recombine those into clusters. So we say that we want block 1, 2, 3. But actually, our file IO might say, well, we want cluster 56, which is block 1, 2, 3, 1, 2, 4, 1, 2, 5, and 1, 2, 6. So we've got lots of different ways of approaching this. Some applications will actually say, please don't partition your disk. So point me to, please don't put a file system on your disk. Point me to a partition that's for me, and I will set that up in my own way for speed, for better access, for whatever it happens to be. So some applications actually want raw disk access. And as we've said before, we have a bootstrap loader that will actually start loading the blocks from the disk. So we need something in there that allows us to get access to that disk. So we'll have, for example, on Windows, a master boot. Which says, here's the code that we're going to use when we're booting. Here's the partition table. Which partition do we want to run? So we've already said we've got a physical disk. We can split it up into multiple partitions. We don't even need to store the same operating system on them. Partition 1 could be Windows, partition 2 could be Linux, partition 3 could be whatever you want. And our master boot record can say, okay, which one of these do we want to boot up from? And when you start up, you say boot Windows, boot Linux, boot whatever. We are also going to probably want some swap space. So we talked about that when we were doing virtual memory. And that's a special case of our file system because it's usually quite big. We want it all contiguous so we're not slowing things down. And there's different ways of doing it. Some operating systems have it in a separate partition that you never access. Some operating systems use it as the same partition, but they set it up quite early so that it's at the start of the disk and it's contiguous. It really does depend on the operating system and what you want to do. And it used to be that you still can actually, but quite often Windows would pop up and say things like, I've run out of swap space. Would you mind if I made the swap space file larger? You go, oh, no problem, on you go. And it would extend that swap space. Now that's hidden. Your swap file on Windows changes according to the requirements of the operating system. And often you're not even asked. You set a limit somewhere in the settings, but it just manages it within that. Linux can have multiple swap areas. Because why not? Someone's pointing out that restore partitions don't always work, and some companies blackmail you into buying a restore CD. I won't mention the name since how this is going on YouTube. I think we all know who you are. And finally, we can set up something called RAID. RAID is a redundant array of inexpensive disks. So we've talked before about how we could have a volume spanning over multiple disks. So say you need 10 terabytes of storage. Now, a 10 terabyte disk actually is far more expensive than buying 3 4 terabyte disks, just because of the way the manufacturing works and all that kind of stuff. So why not get the operating system to say, oh, you've got 3 4 terabyte disks. Maybe I could just have them as an array, and you don't need to know anything about it, and we'll just call them disk. And we'll work out where it's going to go. And I said earlier that we might be able to speed things up. So there's different levels for RAID. So maybe instead of storing every file on a specific disk, we deliberately split it over all of the disks so we can do parallel reads and speed up our reading. Maybe we could store it in more than one place. So instead of having 3 disks, we have 6. And every time we save it to one disk, we save it to a backup disk. So it's stored twice. Maybe you could get more sophisticated than that, and rather than just having the main and a copy, maybe you could use some sort of algorithm which allows you to spread the data over multiple disks, and then if you lose one of the disks, you can actually use that algorithm to recreate the bit that you're missing. So you have a redundant algorithm to fill in the gaps. So go and have a look at RAID and go and have a look at the different RAID levels, because that's what RAID can do for you. And of course, it means that you have less chance of losing your data. If you have one disk, that disk can die. And if you have lots of disks can die. But actually, on average, it will get bigger because that's the way the averages work. Which means that your data is safer. So the mean time to failure, the mean time to repair, and the mean time to data loss all get better. And if you can use a disk controller, a RAID disk controller, to control all these disks and chuck in some memory so that you can have some buffer, some cache in there, where you can get massive speeds. As I say, go and have a look at different levels of RAID. So whether they're doing mirroring, shadowing, blocked interleave parity or whatever, it means you get to this place where not only is your data safer, you actually get RAID systems, and you can buy them in wee cages where you plug in disks. You can actually get to the point where if one of your disks dies, you pop out the disk that's broken and pop in a replacement. And RAID then just refreshes. All without turning off the machine. It's called hot swap. And you can just continue working. There's an example of one that's going on eBay just now. You need to be careful with some of the cheaper ones though, because they don't always have, as you can see from this, it's not just about the hardware, it's about the software, it's about having the RAID software working. So it really, as Fraser says, it depends on your use case. So for example, my NAS has 2 disks in it, and I just use them as mirrored disks. So I've cut in half the amount of data that I can store, but each data is stored on 2 disks. So it just basically gives me automatic backup. So it really does just depend what you want to do. And I almost finished by 1 o'clock, not quite, but almost. Does anybody have any questions? Okay, let me stop the recording then.